A fully loaded freight train, thousands of tons, reaches a century-old bridge at full line speed. The driver doesn't brake. He's not supposed to. His rulebook, written by the engineers who assessed that structure, says maintain speed. Your instinct says that's reckless. Slower is safer. Less weight per second, less stress, less risk. But railway bridges weren't designed for caution. They were designed for a specific moving load at a specific speed. And here's what no one expects. Under certain conditions, slowing down on the span doesn't reduce the danger. It introduces forces the bridge was never built to handle. A freight train carrying 10,000 tons of cargo approaches a steel truss bridge built in 1920. The operator does not ease off the throttle. There are no yellow warning signals, no automated brake triggers at the approach, and no sudden commands from dispatch. Instead, the train enters the first span at 60 miles per hour, the exact line speed authorized for this segment of the corridor. This number is not a casual choice or a limit of the locomotive's engines. It is a strictly controlled operating value, calculated and approved by structural engineers long before this specific trip began. To the driver, the century-old bridge is not a hazard requiring caution. It is simply another pre-approved section of the track. Yet, to anyone watching from below, this lack of braking feels incredibly wrong. Everyday experience on roads tells us that heavy loads must slow down for structures. But on the rails, the driver keeps moving forward at speed. This apparent inaction exposes a fundamental rule of railway physics. Traveling over a bridge at a steady pace is highly predictable, whereas changing that motion might be the very thing that threatens the structure. Initiating deceleration while traversing a bridge can be more structurally demanding than continuing at a constant, authorized speed. This is not a claim that high velocity is inherently safe, nor is the practice of maintaining speed a universal rule. If a signal changes, an obstacle appears, or immediate danger threatens the track, emergency braking remains essential and non-negotiable. However, for a train already operating safely within its approved limits, a sudden change in speed alters how the structure performs. Slowing down does not automatically increase safety. Instead, the transition from one speed to another alters the physical state of the system, introducing forces that do not exist during steady-state transit. While a constant speed represents a balanced equation, changing that velocity changes everything. This raises a fundamental structural question. What happens to a bridge when a multi-thousand-ton vehicle changes its speed mid-span? And why does a steady, rapid crossing keep those hidden forces at bay? Bridges are among the most heavily monitored assets on any rail network. Their structural integrity is constantly tracked through physical inspections, maintenance records, and strict operational controls. While early historical records sometimes associate these structures with catastrophic failure, actual accident databases show that collapses are rarely simple events. When metallic spans do fail, the causes are almost always foundation scour, material fatigue, or design limits, not speed. Even the 1879 collapse of the Tay Bridge was not caused by a train traveling too fast. The official inquiry blamed weak wind bracing, defective cast iron lugs, and poor inspection standards during an extreme storm. The disaster served as a warning about structural assumptions under lateral wind loads, not velocity. Modern railway management relies on this distinction, shifting the focus to how an agency calculates exactly what a span can carry. Our instinctive relationship with speed is forged almost entirely on the highway. If you are driving a car or a heavy truck toward a narrow or aging bridge, your natural reaction is to lift your foot off the accelerator and press the brake. This response is entirely rational. In road transport, lower speeds directly translate to safety. By slowing down, you dramatically reduce the kinetic energy of your vehicle, which decreases exponentially with every mile per hour you shed. If a hazard appears on the span, a slower vehicle gives its driver more time to perceive the danger, steer away, or bring the vehicle to a controlled stop, even if a collision is unavoidable. The force of the impact is vastly diminished, saving lives and protecting the bridge's guardrails and supports from catastrophic damage. On the road, going slower is an uncomplicated way to reduce physical stress and lower the stakes of any unexpected event. However, applying this highway mindset to a multi-thousand-ton train reveals a major disconnect between road traffic and railway physics. A road vehicle is a self-contained, highly localized mass that relies on steering and rapid friction changes to navigate. When a driver slams on the brakes, the car undergoes a sudden shift in balance, transferring its weight forward onto the front tires over a tiny patch of pavement. A train, by contrast, is a vastly different physical entity. It is an incredibly long, continuous chain of heavy segments, with its immense weight distributed across dozens or hundreds of individual axles. Because of this distribution, a railway bridge does not experience a train as a single, massive blow. Instead, the structure registers the train as a highly organized, rhythmic sequence of individual axle loads, arriving one after another. The bridge deck, the underlying steel girders, and the supporting concrete piers respond to this sequence in real time. The bridge's response is governed by both the total mass of the train and the precise spacing of those individual wheel loads. This means that speed changes both the size and the precise timing of the forces acting on the bridge. As each axle rolls onto the span, it sends a wave of energy through the structure. If the train is moving at a constant, predictable rate, these pulses of energy flow through the bridge in a highly patterned way. At this level of scale, the train and the bridge behave as a single unit. They function together as a connected mechanical system, where the movement of the train and the elastic flexing of the steel and concrete are bound in a continuous physical dialogue. The common assumption that slowing down is always safer ignores how this coupled system operates. To see why a fast, steady crossing is often the gentlest path across a span, we must examine what happens when this carefully balanced mechanical relationship is suddenly disrupted. A train parked on a bridge represents a straightforward structural problem. It is a dead weight, a static load that exerts a constant, unchanging downward force on the steel and concrete below. But the moment those wheels begin to turn, the physics of the bridge shift entirely. A train crossing a span at 60 miles per hour acts as a rapid series of physical impacts, a moving sequence of axles that creates an entirely different structural case. As each set of wheels rolls onto the span, travels across, and departs, it introduces forces that fluctuate in real time. The bridge deflects downward, springs back upward, and vibrates. This motion-related increase in structural stress is known as dynamic load amplification. It represents the divergence between a load placed gently upon a structure and that same load rolling across it at speed. This amplification is not a simple, fixed number. It is a complex, fluctuating value shaped by the physical relationship between the vehicle and the structure. Several factors dictate this behavior: the length of the span, the speed of the transit, the precise spacing of the axles, the overall mass of the train, the behavior of the locomotive suspension, the damping characteristics of the bridge, and even tiny irregularities in the track itself. Engineers understand this dynamic response as the static weight of the train multiplied by a specific dynamic effect factor, because calculating these variables for every single crossing is highly complex. Standard design codes provide simplified formulas to ensure bridges are built with a safe margin. In the United States, the American Railway Engineering and Maintenance of Way Association, or AREMA, uses a classic impact formula: 15.4 divided by the span length plus 38, expressed as a percentage. For a short 30-foot bridge, this formula adds a penalty of about 30% to the static load, while on a much longer span, the impact calculation drops significantly. Across the Atlantic, European standards, or Euro codes, approached the problem using a dynamic factor represented as 1 plus phi, requiring exhaustive analysis for highly sensitive high-speed lines. Rather than universal laws, these formulas serve as context-specific guidelines designed to protect different types of infrastructure. Some might assume that building an exceptionally stiff bridge eliminates these motion-induced vibrations entirely, but structural stiffness only dampens the effect. It does not erase it. Even the most rigid steel girder still experiences some level of dynamic amplification when thousands of tons of metal roll across it. The train and the bridge remain locked in a physical relationship where movement itself changes the load, forcing engineers to design not just for weight, but for the complex physics of constant motion. An authorized operating speed is not an arbitrary limit. It is the output of a precise structural assessment. Engineers do not design for a generic train. Instead, they evaluate each bridge against highly detailed load models that replicate the exact types of traffic the line will carry. There is no single, universal speed setting that applies to every structure. Rather, each span is calculated using specific assumptions about axle loads, train formations, track quality, and structural health. In the United States, the primary reference for these calculations is the Cooper E80 design load, which simulates a series of 100 kip axle loads representing the heaviest freight locomotives. Across the Atlantic, European engineers rely on a different set of standardized load cases. Load Model 71 represents standard passenger and freight traffic with a 4-axle, 1,000 kilonewton vehicle. For heavier or continuous configurations, design rules require load models SW0 and SW2. When line speeds exceed 200 kilometers per hour, European standards mandate the high-speed load model. This framework uses two universal train configurations, HSLMA and HSLMB, with variable passenger coach lengths and axle spacings to model the rapid, cyclic forces of articulated trains. For high-speed operations, engineers cannot rely on a simple static impact percentage. They must run a detailed dynamic verification to calculate how the span reacts to the precise timing of those incoming axle loads relative to the bridge's own natural vibration frequency. This process establishes the authorized speed limit as a customized operating value for that specific asset. When a train crosses the bridge at this designated velocity, the entire system behaves exactly as the design equations intended. The train isn't fighting the bridge, it is completing an equation the bridge was built to solve. This smooth, uninterrupted transit represents the expected baseline state of operation. But that balance is predicated on a constant, predictable motion. What happens to the structural math when the train stops following this expected pattern and begins to change its speed? The moment an operator applies the brakes, a new physical force takes over. Instead of just pressing down on the rails with its immense weight, the decelerating train begins to drag the entire bridge along with it. This horizontal action, known as longitudinal force, acts along the line of the track, rather than downward through the axles. During deceleration, the friction at the wheel-rail contact zone creates a powerful rearward reaction. Rather than dissipating harmlessly, this energy travels. It transfers directly through the rail fasteners, passes into the bridge deck, and drives into the bearings, piers, and eventually the massive concrete abutments at either end of the span. Field measurements illustrate the physical scale of this transfer. In specific structural studies of mainline bridges under heavy braking, engineers have recorded longitudinal forces ranging from 20 to 150 kilonewtons. This value is not a universal rule, and the exact force depends on a complex web of variables. The overall length of the train, the distribution of the braking systems, the steepness of the local gradient, and the relative stiffness of both the track structure and the bridge supports all dictate how this load distributes itself. For bridge designers, Managing this horizontal thrust is far less routine than supporting a train rolling steadily across the span. Smooth, constant speed transit is dominated by vertical forces, which are highly predictable and easily absorbed by the deep steel girders and concrete columns. Braking, by contrast, introduces an asymmetric, transient load path. It forces engineers to design for combined load cases where vertical gravity and sudden longitudinal thrust act on the structure simultaneously. While braking is a standard design action and not automatically catastrophic, it forces the entire bridge to work significantly harder than it does during a simple, uninterrupted crossing. Continuous welded rail forms an unbroken steel corridor across the landscape and over the bridge itself. Instead of traditional jointed tracks with gaps that allow individual rail segments to expand and contract, modern corridors weld these rails into miles-long continuous ribbons of steel. This creates an uninterrupted longitudinal pathway, but it also means the track cannot easily relieve its internal stresses. To keep the track stable, the rail must be bound tightly to the bridge. This connection is a complex structural assembly consisting of the rails, elastic fasteners, sleepers, ballast, or concrete slab, and the underlying deck. These components do not function in isolation. When a train accelerates or brakes, the horizontal forces do not stay localized under the wheels. Instead, the relative stiffness of the fasteners, track bed, bridge bearings, piers, and concrete abutments determines how this energy disperses. This physical link is governed by rail structure interaction. Under the International Union of Railways, or UIC standards, the track and bridge are analyzed as a single, coupled system. This coupling is critical when dealing with thermal forces. The internal axial load of a restricted rail is represented by the formula. Normal force equals the elastic modulus of steel times the cross-sectional area of the rail, multiplied by the coefficient of thermal expansion and the temperature change. But this mathematical ideal only holds under the actual physical restraint conditions of the bridge deck. While a smooth transit rolls over this unified system with minimal friction, braking and traction actively stress the connection, turning a stabilizing track system into a direct conduit of horizontal force. Every bridge possesses its own set of natural vibration modes, much like the strings of an instrument. When a train moves across a span, the repeating sequence of its axle loads acts as an external force, tapping the structure at a regular interval. This rate of impact is not random. It is governed by a basic timing relationship. The arrival frequency equals the train speed divided by the distance between the axles, or F sub A equals V divided by D. Here, velocity is the variable that directly controls how rapidly these heavy wheel loads strike the bridge deck. If the train travels at a rate where this loading frequency matches one of the bridge's natural vibration modes, the system can enter resonance. In this state, even modest forces can begin to multiply. Yet this critical response is not a simple function of speed alone. It is determined by an intricate network of physical factors, including the bridge's natural frequency, stiffness, mass, and damping capacity, alongside the train's specific configuration, its vehicle suspension characteristics, and the overall quality of the track. Because of this complexity, managing resonance is not left to driver guesswork or sudden onboard adjustments. Engineers use precise mathematical models to evaluate these relationships long before a route is cleared for service. By tuning the stiffness and mass of the bridge during the design phase, and by implementing formally calculated speed limits, operators ensure that standard trains operate safely outside these specific vulnerability windows. On high-speed lines, resonance is an engineered-out exception, not an inevitable hazard of rapid transit. Slowing down does not reduce the weight of the train or decrease the number of axles rolling across the rails. Instead, reducing speed increases the residence time, the total duration of the train-bridge interaction. When a multi-thousand-ton load remains on a span longer, The structural elements must support that mass for an extended period. This longer occupancy changes the duration and overlap of the bridge's internal stress cycles. In specific structural models, this prolonged exposure can actually generate more fatigue cycles rather than fewer. Fatigue damage is not a simple calculation of speed. It depends on the stress range, the specific structural details, traffic frequency, and the existing physical state of the bridge over its entire service life. Leaving a massive load on the structure longer provides no automatic structural benefit. Any change to a train's operating speed must stem from a formal engineering reassessment of these variables, rather than a driver's split-second choice to slow down. This requirement for calculated, official operating limits explains why trains sometimes do travel slowly over specific compromised spans. Trains do, of course, sometimes slow down on bridges. If you stand near a rail line long enough, you will eventually see a heavy freight manifest, or a passenger service creep across a span at a fraction of its normal velocity. But these slow passages are not an argument against maintaining speed. They are a formal exception to the rule, dictated by temporary speed restrictions. When an infrastructure manager like BNSF or Union Pacific issues a temporary order, they are reacting to a specific, documented change in the bridge's physical state. It might be a crack found during a routine inspection, localized corrosion in a steel girder, or a shift in the underlying soil. This is not the driver choosing to be cautious. It is an engineering recalculation. When a structure's physical capacity changes, the math that governs its authorized speed must change with it. In October 2020, on a rail corridor managed by Union Pacific, inspectors discovered localized steel fatigue on a 70-foot deck plate girder bridge. The bridge had an original assessed line speed of 40 miles per hour. Following the discovery, the railroad immediately issued a temporary restriction, reducing the authorized speed to 10 miles per hour. This structural trigger changed the math. The 10-mile-per-hour limit was not an appeal to driver caution, but an engineering control designed to lower the dynamic amplification factor to near-static levels. Once rehabilitation work was completed and verified by structural engineers, the temporary restriction was lifted, and the original 40-mile-per-hour design speed was restored. This type of controlled deceleration is fundamentally different from a driver braking on the bridge itself. A temporary speed restriction is issued long before the train ever reaches the span. The train's speed is reduced on the approach, meaning the vehicle enters the bridge at a steady, lower velocity. There is no sudden transfer of horizontal braking force, no unexpected longitudinal thrust on the bearings, and no surprise surge of energy through the continuous welded rail. The train is still crossing at a constant, predictable rate. It is simply completing a different, more conservative equation. Slowing down under an official order is a calculated revision of the system's limits. It does not prove that driving slowly is inherently safer for a healthy bridge. Instead, it demonstrates that safety on the rails always relies on absolute predictability. When a bridge is compromised, the infrastructure manager resets the parameters so that the train's passage remains perfectly aligned with what the weakened steel or concrete can handle. Once the repair crews finish their work and the structure is verified, the restriction is lifted, the design speed is restored, and the trains resume crossing at full throttle, exactly as the equations intended. Every bridge functions as a fixed bottleneck on a high-capacity route. When an infrastructure manager reduces a span's authorized speed, the impact immediately expands far beyond that single stretch of steel and concrete. A single localized deceleration ripples backward through the entire corridor, delaying following trains and locking up signaling blocks for miles behind. These operational delays quickly cascade, disrupting regional timetables for hours and costing operators significant sums in lost capacity. Yet these heavy operational penalties are entirely separate from the structural safety calculations. A railway network enforces strict, centralized protocols, rather than relying on a driver's personal judgment or improvised caution. If a bridge is compromised, the temporary slow order remains firmly in place while physical analysis, repair, or engineering reassessments occur. This restriction is not a casual precaution, but a formal, calculated intervention. Safety decisions on the rails never compromise structural integrity to preserve corridor throughput. The entire system is built to favor absolute, predictable engineering controls, absorbing the logistical and financial costs of a delay to ensure the physical limits of the bridge are never violated. The ultimate responsibility for this predictability rests not with the person in the cab, but with the infrastructure manager. Behind every train maintaining its speed is a continuous network of diagnostics, physical inspections, and data tracking. Scheduled inspection regimes constantly search for physical deterioration, structural shifting, and localized damage, ensuring the bridge's physical state matches its design parameters. These physical checks feed directly into structural assessment records, which define the precise operating boundaries for every segment of track. To supplement visual inspections, many networks deploy active load monitoring systems. Sensitive instruments permanently attached to key steel and concrete members measure real-time strain, acceleration, structural displacement, and thermal changes under the weight of passing traffic. This incoming data is paired with advanced fatigue modeling, which calculates how millions of repeated axle passes degrade the metal over a bridge's decades-long service life. All of these inputs compile into centralized bridge management databases. Here, engineers cross-reference actual axle weights, locomotive designs, recorded speeds, and maintenance schedules to ensure the operational limits are never exceeded under applicable railway requirements. Maintaining a consistent speed across a span keeps the entire system functioning safely inside this carefully calculated envelope. When a freight manifest rolls across a century-old river crossing at 60 miles per hour, the lack of braking is not an act of blind faith. It is the final visible link in a highly regulated chain of institutional oversight. The safety work has already been completed long before the train arrives. The driver is simply executing a pre-solved equation. The train maintaining its pace across the bridge represents absolute compliance with a calculated engineering state. The idea that trains never slow down on these structures is a useful provocation, not a literal, universal law. Speed is not inherently safe on its own. Rather, a steady transit remains entirely conditional, dependent on the constant assessment of axle loads, train configurations, and the real-time physical condition of the steel and concrete. When these elements align, the entire system operates exactly as planned, turning what looks like unnecessary speed into routine physics. Safety does not require constant braking. The question was never, why don't trains slow down? It's why we assume safety looks like caution, when in engineering it usually looks like predictability. Every day, thousands of trains cross aging spans without hesitation, relying not on human intuition, but on unyielding mathematics. As our global infrastructure faces unprecedented demands, this reliance on operational consistency only grows. The train isn't fighting the bridge, it's completing an equation. Ultimately, the question was never why trains don't slow down. It's why we assume safety looks like caution, when in engineering it usually looks like predictability.